Hi everyone, and welcome to the section 8.1 video. In this video we're going to be talking about sequences. So let's just go straight into the definition. A sequence can be thought of as a list of numbers written in a definite order. So this notation A1, A2, A3, these numbers here are just telling you, where you are in the list. So this is the first number in the list, the second, the third. That's all those numbers are. And then A1 will be just the first number in your list of numbers. So here's a sequence of numbers. 1, 1, 1, 1, 1, 1 forever. That's a sequence, just a list of numbers. There's others. You can think of all kinds of fun sequences. 1, 2, 3, 4, 5, and so on. You can do 2, 4, 6, 8, whatever you want to do. Sequence of numbers. What we're going to be often dealing with here is these sequences, lists of numbers, are going to have some pattern to them. So, and we're going to be working with the pattern itself. Okay, so we can, it's a good thing to think a little bit about the patterns here. So, for example, this first sequence I wrote down is just 1, no matter where I am in the list, right? This next one, right, I add 1 each time I go down. This one, so these are multiples of 2. So the first one is 2. The second one is 4, 6, 8, so multiples of 2. So it's then nice to be able to take in a sequence and be able to write down a formula for it, okay? So there's this notation down here that's going to be really nice for us to use. And what you'll do is, instead of writing out like we did up here, instead of writing out the list, some of the list that implies, what the pattern is, and then putting ... to say like, okay, now keep going. We don't do that. What we'll do most of the time is use this notation where we've got these little squiggly brackets, and what we do here is we write down a formula for the general nth number in the list. And then you can plug n in and tell me what the number is going to be. So, for example, that first sequence that we had done, 1, 1, 1, 1, forever, then this is going to be the sequence 1. Because it actually doesn't matter what n is, right? I'm just always 1. And that's kind of a weird one, but let's try the next one. 1, 2, 3, 4, 5, so on. This is the sequence given by n. Because remember, n is our counting variable. N is 1 here. So ready, write that down next to this. So here we go. We've got the sequence pieces here. N is 1 here. N is 2 here. N is 3. N is 4. N is n. This is a little bit weird to use n is n here. N is usually the number you use for counting. So we should probably use a different letter, but it's fine. So n is counting where you are. And then it's just like a dummy variable, so that's what we use here for the general term. So if I want to know what the value of the sequence is when n is 5, I just plug into this formula given. The 1, 2, 3, 4, fifth number is 5. Okay, what about the evens? Maybe that one will be a little bit more instructive. The first couple are a little bit, whatever. Okay, I need a formula. Given n is equal to 1 for this one, 2 for this one, right? So second spot, third spot, fourth spot. I need you to give me a formula that produces the first spot gets 2, the second spot gets 4, third spot gets 6, fourth spot gets 8. So we already said that that's multiples of 2, so then we will write this as 2n. Because if you give me a spot in the list, n, all I have to do is multiply by 2 to tell you what number goes in there. You give me 3, 2 times 3 is 6. Boom. So that's a useful thing to be able to do, is to kind of think through what the number should look like here, what the pattern is. If I give you a pattern, being able to think about what that list will look like, and vice versa. So just a useful thing. This idea is going to be useful when we get to series in 8.2 and then the rest of the chapter. So it's an important idea to be comfortable with this notation. Okay, so what's the big thing we are going to talk about with these lists of numbers? So our big thing is, if there is a pattern to this list, we are interested in the long run behavior here. So hopefully remember from pre-calc, you remember the term long run behavior, right? And this is something we talked about with functions. This is something we talked about when we learned about limits in Calc 1. What happens to my thing? Thing here is sequence. Thing in Calc 1 and pre-calc was a function, right? F of x usually. What happens to my sequence as I start plugging in bigger and bigger and bigger inputs? And so if it's helpful, because this is a function, you can think of the sequence as a function. Look right here. It takes in whole numbers, 1, 2, 3, 4, and spits out, for each one of those, it spits out a number. Pew, pew, pew. So that is a function. Now, it is not a function like we're used to for the most part, right? Because the functions we're used to are defined on not always the real numbers, but usually are defined on at least intervals of the real numbers. These are not. They only take in whole numbers, okay? So that stinks a little bit, because then things that we might know about functions in long-run behavior, we can't necessarily just jump to use those, right? Any tool that we would use to talk about long-run behavior of a regular quote-unquote function from pre-calc or Calc 1, anything like that relied on continuity, differentiability, anything like that, we can't use that here, because this sequence only takes in 1, 2, 3, 4, 5. It's not continuous on the real numbers, so we have to be super careful there. But we're going to deal with that in just a second. So don't worry, not all is lost from our calculus knowledge. But just to get back to this definition, we are interested in the long-run behavior of our sequence. What do we call that? Well, for the 10 millionth time in a calculus class, we call it a limit, and we use the same limit notation. Give me a sequence. Here's the formula for the general nth term, right? As n gets bigger, as I move down the list. So what's this saying? As I look down the list, as I keep looking down the list, I ask the question, are the numbers that I'm looking at, are they approaching a value? Are they getting smaller towards 0, right? Smaller, smaller, smaller towards 0. Are they getting bigger, but it seems like there's a clear cap to that? Are they seeming like they're approaching up to 1, but never maybe going to hit it? Just like you did limits before. Functions could have limits from Calc 1. Sequences can have limits, and it's a very, very similar idea. Let your input get bigger. What does the function seem to be doing? So, this is not a new idea. If the limit exists, we say the sequence converges. Now, I'm being very over-dramatic about when I just said that with underlying, because we are going to have two different types of convergence in Chapter 8. A sequence converging, just a list of numbers converging, and then we're going to talk about, in 8.2, something called a series, and a series converging. They are connected, but they are different. So, I'm underlining this word sequence because you're going to want to be saying the sequence converges or the sequence diverges, just to keep it straight in your mind when you're working in all of Chapter 8. So this is like a little tiny thing to just pay attention to. So I look down the list of my sequence. What's happening? Well, so let me talk to you about a couple of these examples. Let me give you an extra one too, just to get you thinking about some of these different ones we could do. So the sequence 1, right? What was that one? That was just 1, 1, 1, 1 forever. Okay, so then what's the limit? The limit as n goes to infinity of the sequence 1 is 1. Because it's just 1, always. 1, 1, 1, 1, 1, 1 forever. So hopefully that's not too bad to see. And this should be a little bit something hopefully you remember. Limit of a constant is just that constant. Remember when we did that in Calc 1? Oh, okay, so similar. So, okay, good. What about limit as n goes to infinity of the evens, 2n? Well, this is going to end up being infinity, and I haven't proved to you that that's going to be true yet, right? You don't know how to deal with a list of numbers yet. But hopefully just thinking about it, it just keeps getting bigger. 2, 4, 6, 8, and that's never going to stop getting bigger, bigger, bigger forever. So this is going to be infinity, okay? Now what about this one? Limit as n goes to infinity of 1 over n. So what does this look like? Immediately write terms down. We don't need to be superheroes here. Just write the terms down. This limit, so 1 over n, or sorry, this sequence is the sequence what? It's the sequence 1, 1/2, 1/3, 1/4, keep going. So just looking at this list, 1, and then I go down to half, 0.5, 0.33, 0.25. Getting smaller and smaller and smaller, but 1 over n will always be bigger than 0, right? When n is getting bigger and bigger and bigger. But it's still getting smaller. And so hopefully it's not too bad to see that that's going to approach 0. Again, not proving this yet in any way. I have not proved this to you. But just thinking through how we've thought about limits in the past, hopefully these three are okay. So, all right, we've got a sequence, a list of numbers. We can talk about what happens as we go down the list. Does it converge? Does it diverge? So, we've got two pictures here to kind of illustrate what sequences can look like graphically and what they can do. So here's a sequence. Now, we graph sequences by just saying what happens at 1, what happens at 2, what happens at 3, what happens at 4, right? So we should not expect a nice continuous line because the sequence is not defined at 3.5 or 2.5, right? We don't have a definition, so we're only going to have dots here. But as you can see, we're going up and then we're going to go down and we're getting closer and closer and closer to this L. So that graphically implies the limit is L. What about this one? Well, this one's kind of acting a little weird, right? Up, then down, then up, then down, then up, then down. But each time I go through one of these cycles here, cycle, 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 I'm getting closer and closer to L. And that's what matters. Am I getting closer to L as n gets bigger? Okay? And so it can look, the sequences can look very different as long as they have this pattern that emerges getting closer and closer to L, we can say that they have that limit. Now, here is a very important theorem that's going to be so crazy helpful in figuring out these limits. And here is the idea of it, which you might have already kind of been thinking about, possibly. Here's the idea of the theorem before you even see it. When my brain looks at this, and I don't know, maybe it does it for you too. When my brain looks at this, here's what my brain is trying to do. This is what my brain does. It says, I don't like this. I'm looking at this picture, right? Like that was a pretty terrible fitting. I can't draw in lines or follow dots, but hopefully you see what I'm doing here. My brain is trying to just like fit this. Just fit a curve to these dots. Stop giving me dots. And over here, it's like, get this out of here. I don't want you to do that anymore. Just no more dots, fill it in. Okay, well, let's stop here for a second. If we do that, these now have become continuous functions defined based on our drawing on all of the real numbers, at least from 1 to infinity, right? And so we then now have the full power of calculus, Calc 1, and calc limits, and L'Hopital's rule, and everything is on the table now for figuring out what this limit is. And so I was trying to hint that earlier, that like, oh, these kind of look like functions we've seen before. And your brain might already want to do that. And luckily, the theorem below tells us you can do that. So this theorem number 2, it's number 2 in that section in the book. The theorem says, if you have a function f of x, and the limit as x goes to infinity of that function equals L, if it happens that your function and a sequence, a sub n, overlap. So overlap being, if I have the dots here for a sub n, then the function and the dots agree at every whole number. So if my function and my sequence actually agree for every whole number where the sequence is defined, then it just so happens that they will have the same limit. So why is this so powerful? Well, this is so powerful because this allows this question, which we're maybe a little unsure, how do we even figure this out? This question can be transformed into this question. X goes to infinity of f of x. And over here in this question, right, I've got my calculus tools. So I take out my calculus tools, my L'Hopital's, everything we know about limits from Calc 1. I take those tools out and I use it to solve this limit. And then I take that and I transport it back over here to the sequence, and they're going to have the same limit. Okay? So if I can find a function that fits the picture I drew, just like up here, the picture I drew being the sequence, the dots. If I can find a function that fits the dots and it has a limit L, then so does my function here. Okay? So, you know, hopefully that's not too bad to see by just thinking, you know, fill in the picture. There's a theorem that tells us we can do that. So this video is going to be just a ton of examples, right? We're just going to crunch through a bunch of examples of these. And so we're going to get a bunch of different tools for working with sequences, like the theorem we just got. We're going to try to apply them. So we have a sequence here. The question is, what happens as n goes to infinity for n cubed over n plus 1? Okay. Now, here's the thing. Build some intuition here. Just take a guess. What do you think is going to happen? Start plugging in big numbers. Well, a big number cubed is going to be pretty big. A big number is, okay, that's still a big number on bottom, right? But a big number cubed is definitely going to grow faster than just the big number, right? 10 cubed is a lot bigger than 10. 100 cubed is a lot bigger than 100. 1,000 cubed is a lot bigger than just 1,000. So just intuitively, that's making me think that the top's going to grow faster than the bottom. So here is my guess. So this is, I'll put this in a different color. Here is my guess. Gary's guess. I'm going to guess that this is going to go to infinity. Gary's guess. Okay, so that's my guess just by thinking about what this is. So how do I actually do this? Well, what we can do is we can say, let's convert this limit into a function such that this function I just wrote in here and this sequence will agree whenever I plug in a whole number. So if I plug in the number 2 into this sequence, that's going to be the same as plugging in the number 2 into this function here, x cubed over x plus 1. Okay, so I've picked a function that agrees with this. How did I do that? Just change n to x, that's it. That's the simplest way to do it. All right. So, okay, if I can talk about this limit, I can talk about this limit. Now, how do we talk about this limit? We have got so many ways of doing this, right? Way number 1, this is rational, right? So all I have to do is take the highest power on top and compare to the highest power on bottom. 3 is bigger than 1, so this goes to infinity. So this is something we learned about in pre-calc. If you get a rational function and the power on top's bigger, you're gone to infinity. Okay, what's another way? Well, another way here, right, is to use L'Hopital's rule. Right? How do you use L'Hopital's rule? Well, try plugging in the actual limit here, right? Plug infinity in. I know I'm being a little crazy here with plug infinity in. That doesn't really make sense. But just symbolically do that manipulation so you can see. If you do that, you're going to get infinity over infinity. Oops. And that is primed for L'Hopital's rule. If you get infinity over infinity, that's indeterminate. We have no idea what's happening. So L'Hopital's rule says that this limit, as x goes to infinity, of x cubed over x plus 1 is equal to L'Hopital derivative, so don't forget your limit, do the derivative of the top over the derivative of the bottom. And now this function, this new function inside, you take its limit, and this is just infinity. So here is where this gets tricky. How do I, go all the way back? So let's see where we are right now. The limit of 3x squared is infinity. But by L'Hopital's rule, that tells me the limit of x cubed over x plus 1 is infinity. L'Hopital's lets me drag this backwards to here. Okay, but theorem 2 tells me that this limit is actually the same as this one. So I go all the way from this answer, I use L'Hopital's to drag it back here, and then I use theorem 2 to drag it all the way back here. And so by theorem 2 and L'Hopital's rule, right? What do we know? The limit as n goes to infinity of n cubed over n plus 1 is infinity. So it might seem like I'm being a little bit, I'm overdoing it a little bit with this, but it's important to keep yourself really focused on where you're starting, what's the thing you want to answer, what methods, what theorems, what rules you use to take any step you take in here, and then to be very clear about how you did that in your answer. I used theorem 2 to go from here to here. I used L'Hopital's rule to go from this limit to this one. I've clearly said that those are the two things I've used, and I've made my conclusion about this limit. So I'm not going to talk that much about each one of these at the end, but I will be referencing what we're using, because it's important to keep yourself grounded in the problem, because we're going to be taking lots of steps, going lots of different places. But there we go. Just like my guest said, this is infinity. Okay, so here is another tool. This is called the squeeze theorem. And the squeeze theorem says if you end up with 3 sequences, A sub n, B sub n, and C sub n, these are 3 different sequences, okay? If at some point past some n0, so this is when it starts. And what do I mean by it? I mean this set of equalities. So for a little bit, if A and B and C are all mixed up, like A is the biggest and then maybe C is next and B, that could happen for a little bit. But as long as at some point this holds all the way out to infinity, and these two, the smallest and the biggest, have the same limit, L, that forces the middle to have the same limit. So here's the picture. A sub n is going up, but it seems like it's kind of flattening out at some limit L. C sub n, it's going down. It's still bigger than the other two, but again, it seems to be flattening out at some limit L. Well, B is inside. It's stuck in there, right? That's what this says. B sub n, for any n, is going to be, any n big enough, is going to be stuck up in there. It can't get out. So C sub n is smushing it to L from the top. A sub n is smushing it from the bottom. And so B sub n gets smushed from both sides, push, 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 towards L. So this is a super, super useful idea, really, really useful. This idea actually is something that you can look in the book is useful for integrals as well. So when we have integrals that involve infinity, we can use a very similar theorem to compare to other integrals. So this is something you can go check out there, right? But for us now, it's going to be super, super useful. And the reason it's useful is, and we'll do an example just in a second, B sub n is going to end up in a lot of these problems making us real sad looking at it. We're going to look at a sequence B sub n and be like, pass. But instead of passing, we're going to say, you know what? I think I can find an a sub n and a c sub n that make me pretty happy. These aren't too bad to look at. I know what's going on with those two. And if we can pick these correctly, then what we'll be able to do is we'll say, okay, you know what? This one's smaller than b, this one's bigger than b. I know what these two are doing. They're both going to L, the same number. And so that will force b to go there as well. So more complicated, simpler, and we know what's happening. They're doing the same thing. That's the goal of doing this. So let's do an example. So, okay, I've got the sequence a sub n equals cosine squared n over 2n. So what is my goal? My goal is to look at this and go, all right, I'm pretty sad looking at this. 2 to the n, okay, that's, there's exponents there, cool. I think I know what that looks like. But then the cosine squared, it's like, oh, I can figure that out. But then I'm dividing. Uh-oh. But we have the squeeze theorem. So all we have to do is take this sequence and squeeze it between two other sequences that are easier to understand. Now, what's going to make this easier? Well, 9 out of 10 students agree that the tears coming from this face are from the cosine. If you don't agree with that, that's fine. Being a 1 out of 10 is often a good thing. But the 9 out of 10 think the cosine stinks. So what do? Get rid of it. Okay? How do you do that? Well, remember, we need to find something smaller and something bigger. Okay? And the way you do that in a lot of these scenarios is you say, well, what do I know about cosine? Go back to your functions, cosine. Forget about square for a second. So what do I know about cosine? Well, I do know that cosine itself is going to be between, and I'll just use the regular function because that's what we're used to right now, -1 and 1. So okay, so if I'm only restricting myself to n, which is whole numbers, then this is still true. Oh, cosine squared though is actually going only between 0 and 1. Aha. So what am I saying here? I'm saying that cos squared n is going to be between 0 and 1. And then I don't quite know what to do with this 2 to the n yet. So I'm just going to leave it. Okay. So, whoa, look at that. We just took this and turned it into two way simpler things. Because 0 over 2 to the n ends up being just 0. Right? Cos squared over 2 to the n. And then I have this to deal with. So immediately, what do I know? The limit as n goes to infinity of 0 is 0. Cool. What about this one? Well, let's do this. The limit as n goes to infinity of 1 over 2 to the n. Okay. Well, so you've got a bunch of different ways to do this. You could use theorem 2 again and rewrite this as x goes to infinity of 1 over 2 to the x. And we know that 2 to the x is going to get really, really big, right? As x gets big. So this is 0. And we're going to actually have a theorem that tells us the same thing in just a second for anything that looks remotely similar to this. But for now, we can just rely on the fact that we knew this integral from this limit from Calc 1. So, okay, that limit's 0. Wait a minute. So you're telling me on top, this goes to 0. This goes to 0. So because this goes to 0 on bottom, this also goes to 0. They're equal by the squeeze theorem, right? By the squeeze theorem, that forces cos squared n over 2 to the n to also go to 0. Yippee. How did I do that? I used the squeeze theorem. I bounded the sequence below and above in such a way that both of these go to the same number, 0, 0. that forces anything in between them to get squished, squished, squished down all the way to 0 as well. Squeeze theorem. Okay, so let's keep going. All right, here's another theorem that's pretty useful. Also useful for trig. Doesn't have to be trig, but is a useful theorem for trig. Functions. If the limit of the absolute value of your sequence is 0, then that forces your original sequence to go to 0. Okay, so we're looking at this. What do I mean by this first? Like, what the heck is this thing, right? What is this sequence? Well, pick a sequence just as an example that has some positive and negatives, right? And I'll do a simple one. So let's let a sub n be, and then we can make this be, just to kind of make it simple, 1, -1, 1, -1, 1, boom, 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 boom. So then if I start taking absolute values of this, it's just 1, 1, 1, 1 forever. I literally just do the absolute value of every single number. That's it. Make every number positive. Done. That's what this means in here. So what this says is, if I have a sequence that, has some ups and downs in it, it goes positive, it goes negative, it goes positive, negative. It could be like positive for a little while, then jump down to negative. That's fine. But if I have a sequence with both in them, this theorem says just forget about the negatives, right? Don't even worry about the negatives. Just only focus on that being positive and solve that. If you can solve that, you can solve the original. So this is just like theorem 2, where we take some limit that might be kind of harder, and we can convert it to something different, and which you're going to see that is true for a lot of these. Okay, so we're going to look at an example here that actually connects to this quick little example we did. And so this theorem can be useful when you have anything with an alternating term. So alternating means positive, negative, so on and so forth. You could start negative, negative, positive, negative, positive. It just alternates positive, negative. That is accomplished by a term like this. So this is important to be able to recognize. And later you're going to be asked to see a sequence or a series, again we'll get to those later, where you see alternating terms, and you're going to need to know how to write that in a form like this. And this is the thing that's alternating. And just like anything with sequences, plug in, right? Plug in 1, that's a negative. Plug in 2, squaring something makes it positive, positive. Plug in 3, negative. 4, positive. So on and so forth. So this -1 to the n gets you alternating. So it's important to be able to recognize that. Okay. So how would we do this? How do we even deal with this term? The way we deal with it is we don't deal with it, because this theorem tells us what we can do is just slap our sequence with absolute values and not worry about it. So by theorem 4, okay, we can focus on the limit as n goes to infinity of the absolute value of our sequence. So theorem 4 says we can focus on this now. Okay, well, what's this going to be? This just takes everything and makes it positive. So that just makes this limit equal to 1 over n squared. Because this -1 to the n, all it did was try to make me positive, negative, positive, negative. Absolute value just gets rid of that. And this one, we're done. This one is 0. And you can do this, a few different ways, but really this is just remembering your calc limits, right? And remembering that as x goes to infinity, 1 over x squared is 0. And remember, we had a rule for this. If you have 1 over x to the power, remember there was a rule here that kind of told us what's going on, right? If you end up with x to a power, and it's a positive power, you're shooting off to infinity. But if you end up with a negative power, or equivalently x to a positive power down here, you're going to 0. So this is just from Calc 1. So, okay, what did we just show? We showed the absolute value of this sequence, the limit is 0. So by Theorem 4, because the absolute value of the sequence is 0, then what do we end up with? The original limit also is 0. And we're done. Ginormous warning here about Theorem 4. So warning, warning. Danger, danger, Will Robinson. That same 1 out of 10 that liked sign, that's the person who just got that. So what does this say? If the absolute value of this sequence, if we take that limit and it's 0, then we can go back to the original. This works only if, when you take this absolute value, you get 0. This does not work otherwise. Very important. Important thing number 2, we always start by having to show the absolute value is 0. Then we can make a claim about a sub n. This does not necessarily go backwards, okay? So just, be careful whenever you see any theorem, right, that's one direction. And I know this is something that you may have never seen before with some of the logic here, but this is an if-then statement. What does an if-then statement mean? It means if we assume this is true, whatever is next to the if, we can then say this is true, okay? But that does not mean assuming this is true tells me the first one's true. You cannot necessarily go backwards, okay? So I know that's super weird and maybe not something you're super comfortable with, but it just is something you have to pay attention to with the order of these things in the theorem. So when you do, and when you read a theorem that says if-then, this one first is the one you have to go find as true. That gives you the second part for free. But it does not mean you can go the other direction. So just a little warning here. So I guess my warning was not drawn down there. Warning. I'll just write it again. Why not? Okay, so let's keep going. So here's another big one. And this, again, ties directly to what we thought in Calc 1. So that's super nice. Let's say you have a sequence of the form r to the n, where r is some number. R is a number. It's a constant. Okay? Well, if you have a number raised to the power n, and again, what's this going to look like? Always draw it out. R squared, r cubed, r to the 4th, ... If you do this, power, another power, then we can say it will be convergent if r is between -1 and 1. It's divergent for everything else. That's summarized right here. The limit of this is 0 in here. The limit is 1 if you're equal to 1, because what's this just going to be? Plug it in. If r is 1, you're going to have 1, 1, 1, 1, 1. We saw the limit of that was 1. If r is between -1 and 1 not including, you're going to go straight down to 0. Plug some numbers in and look, right? In this scenario, r is 1/2. Just plug in numbers and see. 1/2. 1/2 squared. 1/2 cubed. 1/2 to the 4th. What is that? 1/2. 1/4. 1/8. 1/16. Look, I'm getting smaller. I'm going towards 0. So at least you can kind of believe it there, right? So all right, that's nice. It's actually crazy useful, because I can take something like this, use a little algebra magic, and write it of the form r to the n. So how is this going to help you with a problem? You're going to have to look at this and go, this looks to me like r to the n. Okay? Now, here's the thing. Looking like r to the n is good. you've got to make it r to the n, right? You got to make it into that. So, okay, how do we do that? We need a number to just a single n power. Well, I see here a 5 to the n, that's good, but I don't see 3 to the n up here. If I could write it this way, I'd be really happy because I could combine this into 3 over 5 to the n. This is just using exponent rules. So like I'd be super happy here, right? But this pesky plus 2, exponent rules again. I can take that out. How do I combine these? 2 plus n. So I can just go the other way. I can take this plus 2 and peel it out. So this sequence then ends up being 9 times 3 over 5 to the n. Okay. And then it's not quite the limit of r to the n, but if I wanted to do this limit, watch this. Right? This is the limit as n goes to infinity of 9 3 over 5 to the n. Okay, and this works just like it does from calculus. Constant, bring it out. And we're here. And guess what? This tells me that if r is less than 1, between -1 and 1, I'm going to 0. 3/5. 3/5 is less than 1, but bigger than -1. What does that tell me by the above? By this little 7 box here, this tells me that this limit is equal to 9 times 0, which is 0. Boom. So I look at this and I'm like, oh, that really looks like r to the n. Make it r to the n. You might pop out an extra constant, but that's okay because they can be moved out of the limit. Totally fine. Boom. Another crazy useful one. Hold on to this. This is super important. It's going to help you a ton in problems going forward. This section and later. Okay, let's keep going. All right, we've got another one. N cubed over n cubed plus 1. So we're at this point now where it's kind of like we've got a bunch of tools in our toolbox. Now what do we do, right? Like I have just a general problem here. Where am I going? Okay, so a nice way to start a general problem where we didn't follow a theorem, we're not sure what to do necessarily, is to look at this and just kind of like think about it. You know, here's a graph. What's going to happen here? Well, we want to talk about this, right? This is what we keep talking about. So just think about it. What happens as n gets big? N cubed gets big, n cubed gets big. So they're both getting really big, top and bottom. Well, from pre-calc, I seem to remember, right, from my pre-calc days, I seem to remember a rational function. What happens when you have the top highest power and the bottom highest power equal? Do you remember what happens? So what happens is that when that's the scenario in a rational function from pre-calc, we can rewrite it this way, and your limit will be 1 over 1, which is 1. So it's just the ratio of the constants. So remember, from pre-calc, same power top and bottom, you just take the ratio of the numbers, the constants in front. That's your limit. So how does that help us? Well, by theorem 2, we can take this limit instead, x goes to infinity, of x cubed over x cubed plus 1. Okay, and this limit, we have our pre-calc way. We could do L'Hopital's, right? So this would be number 1 way to do this. L'Hopital's would be number 2. You have that method of divide by the highest power. Maybe you remember that, maybe you don't. You just, x cubed is the highest power here, so divide everything in inside the whole limit by x cubed. Do cancellation, see what happens. In any scenario that you do these, you're going to end up with this limit equaling 1. And so by theorem 2, if this limit equals 1, then the original limit equals 1. And if we look at the graph, that seems to fit. I'm increasing, but look how slow that's increasing. 1. Okay, so a lot of what you do depends on building intuition about these sequences and trying to like connect them to either a function from pre-calc or calculus that you're used to, or just another problem you've done, or whatever. So thinking through what's happening here as n gets really big, trying to make the right connection. So let's keep going. Okay, tangent. Uh-oh. This might be a little scary, right? But we've got ways to deal with this. So first things first, here's what I want you to do. Just focus inside. Focus just on this. What do you think is going to happen as n gets big here? What do you think is going to happen to this, right? N goes to infinity. What's this doing? Well, 2 to the n is going to get really big, 8 to the n is going to get really big, but they're both a single power of n, right? So that back to my pre-calc, they're growing the same rate. So shouldn't the n's kind of like cancel and leave just the 2 and the 8? The 2 pi and the 8? Yeah, that's what happens, right? This inside, these are the same power. This is rational, so we know what should happen there. So then you're sitting there like, tan though. Well, there's another Calc 1 rule here that we haven't talked about yet for limits that's helpful. The Calc 1 rule here is that as long as this function is continuous where you're talking, right, where we're discussing, which it is, tangent is continuous for all of the possible values from 1 to infinity here. So because tan is continuous over this range of values, we can do something special here. We can do the just zoom inside and see what happens. So let me write out what we're saying here more specifically. What I'm saying is, let's focus on this calc problem instead. 2x pi over 1 plus 8x. Because tangent is continuous from 1 to infinity, which is the x's we care about, right? And this is defined also on that range, the inside. What we end up being able to do is saying, okay, you can pass, remember, the limit through the function. So this is another one of our Calc 1 limit rules. We can pass the limit through certain functions and just focus on the limit inside. Now, this limit inside, remember, this is just a rational function again, just rational. So however you deal with rational functions, L'Hopital's, the division trick, whatever, it just so ends up happening that this limit inside is going to equal highest power on top is 2 pi x. Highest on bottom is just the 8x. So x to the 1, x to the 1, those are the highest powers of x. We look at their ratio. You can think of canceling them, whatever. But in any case, that's going to go to pi over 4. As x gets really big, this goes to pi over 4. And so all together, we end up with tangent of the limit, which we just saw that limit was pi over 4. And guess what that is? 1. Hey, that looks like 1 maybe? So what did we do? We took this, replaced it with its function version, function defined on the real numbers, not just the whole numbers, used our pass the limit through a function trick, and then saw that it was just a rational function and dealt with it in any of the numerous ways you want to. So again, by theorem 2, because this function, this calc function, its limit's 1/4, our original limit has to be 1/4 as well, with n's. 2 pi x over 1 plus xn. silly is 1/4. So we convert to a function of x's so we can use our calculus tools. We use our calculus tools. We get an answer, right? Did I just say 1/4? 1. How is that 1/4 stuck in my head? Get out of there. Silly. So again, we pass to a function of x's defined not just on whole numbers, right, but all of these numbers from 1 to infinity. We pass to that function. We use a calculus limit rule of being able to take the limit and move it through the function tan. This is rational, so we just compare top to bottom. That's pi over 4. Plug that back into tan, don't forget that. That's 1. And we can bring it all the way back to our original limit. There you go. All right. What about this one? Holy moly. Look at this one. Well, let's look over here. We're bouncing. Bounce. Bouncing. What does that make me think? Bouncing makes me think, I hate it. Let's do this. And this is actually a really useful idea, even though it seems silly. You look at these things, and often you're going to look at the formulas and go, I hate this piece of this. Well, that's usually the thing that you're going to have to use a rule for, to do something with. Often, just try to get rid of it. So, harness the anger towards certain parts of these sequences. Harness your anger towards certain functions and use it as a tool to solve. Negative 1 to the n. Ugh. How do I get rid of this? I got to do the absolute value. And that's going to work, right? That's going to end up working. So we're going to focus on the limit as n goes to infinity of the absolute value of a sub n, which just happens to be drop this piece that's no one likes. So that's n cubed over n cubed plus 2n squared plus 1. Okay. Well, again, rational function. These happen so much, right? So I'm just doing these a little bit quicker. I'm skipping the step where we turn this into x's, right? And the reason I do that is because this rule that we had for limits of functions of x with rationals extends to sequences. So that rule just extends all the way to rational functions of sequences too. So highest power on top, highest power on bottom. Okay, what's happening here? This equals 1. All right. So we're at this point now where I'm trying to say, okay, well, the limit of the absolute value equals 1, so then the limit of the original will also equal 1. I thought this was closer, so this is getting awkward, the slow scroll. But we're going to slow scroll anyway. Reread the theorem. If the limit of the absolute value equals 0, then the limit of the original equals 0. What was my warning? You gotta get 0 if this is going to work. Let's awkwardly scroll back down way too far because I didn't plan this out the right way. Should have been closer. I did not see 0 here. I see 1. This does not work. Big red X. So it's not bad when that happens. I know it's annoying, right? You just did this work and it didn't get you anywhere. You know, that's okay. That happens. That's fine. What you need to do is just, you got to go like, okay, what else can I use here? Like, you run into that, you try a method, it doesn't quite work, it doesn't mean you stop. What can I use here? So let's stop and go back and think about this sequence itself, and we'll use the picture. What is happening when n is an even number? N even. What do I mean by that? 2, 4, 6, 8. Here I am, here I am, here I am, here I am, here I am. Look, so these are all approaching what looks like 1, which is kind of what we had seen here, right? But as I look at only the odds, here I am, here I am, here I am, here I am, I'm actually approaching -1. So we should have been able to see this right from the start that this wasn't going to work, because we need, even if you're going to go up and down and up and down, that's okay as long as those ups and those downs are converging towards 0, or they're both going towards 0. But they're not. In this case, our sequence almost has like two sequences in it, right? It has the sequence that happens at the evens that go up to 1, and it has the sequence that goes on to -1 using only the odd inputs. And so you can almost think of that a little bit like limits of a function, right? The limit of a function before, right, when you were just doing like as you approach a, from the left and right, you've got to be equal. You can't have half of the limit doing one thing and half doing the other. This is the same idea. We cannot have these two separate mini sequences in here doing different things. They have got to both be doing the same thing. And so because of that, this actually does not exist. So the limit of a sub n does not exist. Why? Well, the limit doesn't exist because the limit of just the even terms is 1, and the limit as n goes to infinity, of the odd terms is -1. And these need to be the same. If you're looking for a way to actually write this, here's how you can do it. Limit as n goes to infinity. This is just a useful thing to kind of have in your back pocket. How do I make this subscript even? Like this. 2n. Let me rewrite that so it's not terrible. I can do things like this. I can make this 2n. And so that, no matter what n is, it's going to be only evens. But at the same time, I can rewrite this one, and you've got some choice here actually. Depending on how you start n and how you start your sequence, you can write this as 2n plus 1, or you can also do 2n minus 1. Either one of these, depending on, do you start your sequence at 1 or 0, will only produce odd indices. 1, 3, 5, 7, So this is just useful notation we're going to see later, so this is a good place to bring it up. But because this sequence has these two separate pieces that are doing different things, that have different limits themselves, this limit does not exist. So this is a super tricky one because it looked to be of a form we might be like, okay, yeah, just apply this idea to. But we've got to be flexible here. I apply this idea because it seems like it's going to work. It does not match exactly what the theorem says. Pivot to something else. You got, in this chapter, more than any else, you got to be ready to just pivot out of something. This isn't working, pivot to something else. Like just ditch it, try something else. You got to be flexible with these types of problems. And that happens. We saw that here. Okay, what about this one? So we've got the sequence a sub n equals the natural log of n squared over n. Okay, so we got to think about this. What tools do we have? Well, we've got a bunch of tools. We can consider this, right? We can consider this function and see what happens there. We've got the squeeze theorem. Can we try to squeeze this? This, we're starting at n equals 1. I mean, you probably start this at n equals 2, actually, just because 0, you don't usually start with 0. But in any case, this is positive, also because it's squared. So, doing the absolute value is not really going to help us. And I don't see right away what we could squeeze between. So why don't we just go back to Calc 1 with this function, and why don't we see if we can talk through this limit. So okay, we're back in Calc 1, wherever that was for you. Just put yourself back there. What happens now? Well, just plug in and see what happens. When you plug, again, being a little silly here. Plug infinity into log. As x gets really big, log itself gets really big. Squaring only makes it bigger. So on top, I get an infinity. On bottom, I get an infinity, which screams to me L'Hopital's. So let's do it. That limit is equal to, via L'Hopital's rule, derivative of this. So first write your limit, don't forget that. Drop the 2, plug back in, times 1 over x, derivative of the inside, don't forget, chain rule, over that derivative. So okay, let's do a little algebra here, right? We can do that. This is going to be the limit as x goes to infinity of 2 ln x over x, which again is going to give us infinity over infinity. But we dropped a power of 2, so it does seem like we're going forward. So we have to use L'Hopital's a second time. I'm sure this was your favorite problem when you did this in Calc 1, double L'Hopital's. So you do this again. 2 times the derivative of natural log is 2 times 1 over x. Derivative of x is 1. That gives me limit x goes to infinity of what? 2 over x, which is 0. Okay, so we just did a lot of stuff here. Recap. We took this sequence, used theorem 2 to convert it into a function that agrees on all these n values. 1, 2, 3, 4, all of them agree here. We used L'Hopital's twice to find out that this limit is 0. So then by theorem 2, if this limit is 0, our original one is also 0. The limit as n goes to infinity of, what were we dealing with here? Natural log of n squared over n is 0. Boom. So hopefully you can see how these problems aren't too bad when you break them down piece by piece. But you know, this is why Calc 1, Calc 2, all these things we learned, you've got to get them down. Because look, I just used L'Hopital's twice, and it was a fairly small and quick piece of a bigger problem. You cannot be trying to do these problems and learn these new ideas if you're tripping up on using L'Hopital's rule or taking a derivative using chain rule. It's not going to go well. It's going to be terribly, terribly hard to do this. So you've got to be practicing your derivatives always. Practice, practice, practice. That's so Calc 1. No, it's Calc everything. Just practice your derivatives. But that's it. A lot of rules. I know it's a lot. Just get as much practice as you can. We're going to move to series next, but these rules and these ideas are going to continue. So you're going to get more practice through all of Chapter 8 with them. As usual, let me know if you have any questions, of course, and I'll see you in the next video.